Thanks a lot. Yeah, I was dreaming of flying on the beach at some point this week, and Tyler and I were talking. I was saying, I hope Wednesday afternoon's free, and he said, no, there's a talk even later on. I was saying, oh, he's giving that. Thanks for making it anyway. I appreciate it. Yeah, so okay, let the themes of this talk develop by sort of running with it. So, okay, so let me begin by a kind of a general theme that we can speak about sort of landscapes as a way of depicting certain random objects, I suppose. In a complex, discrete statistical mechanical system, you can write a probability measure in terms of a Hamiltonian and regard that as an energy specified over a landscape. I'm not being, in a sense, too precise here. I just want to convey a picture as much as anything else. For landscape geometry, you have the hills and the valleys here. You're picking points that are much more probable to be in the base of these valleys, with the ground state, the lowest point, minimizing the Hamiltonian H at the base of some valley. And the geometry of the situation can be complex. It may or may not be the case that there are competing valleys that in some sense are geometrically somewhat distinct, close rivals to the status of the minimum, but perhaps at a certain geographical distance, to express it in loose terms. So, a broad theme, broad organization for the talk in terms of three questions one can pose in this context. Is the ground state energy super concentrated? Do we have a situation where a significant random variable, to put it rather vaguely, has the property that the growth in the variance is less than that expected in the classical CLT situation, in which it's linear if I have the n variables. Linear growth in a classical situation, super concentrated. This is a slightly loose mangling of the definition, in fact, but there's certain ideas conveyed by asking the question, is the variance growing at a sub-linear rate? Are there multiple valleys? I already mooted that point in that picture. That's intended to emphasize the possibility that there are several geometrically distinct ways of almost obtaining the ground state energy. Does chaos reign? So this is just an example. If I take critical percolation on the hexagonal lattice in the plane, then that is something in which these black and red tiles are being inserted with half-half probability. And the question is, are we connecting red to red, north to south, or conversely, topological fact, of course, that if we're not doing that, we're connecting black to black, east to west. So if I start noising the system, as people say, in which with independent updates I resample hexagons, then I see some sort of transition. All I'm saying in this slide is that there's a notion of being pivotal, I suppose, and that the red or black status of that hexagon is going to determine the outcome. But it's related to the themes of the talk to start doing updates and to talk about the timescale on which, if we begin with a red connection north to south, that may become interrupted, more or less likely to be interrupted on some timescale by an opposing connection in black in the other direction. Okay, so then imagine that the landscape is some sort of maybe Gaussian disorder, and we find a natural way of noising it. Is that noise something that in just a short period of time its action is going to disrupt the status that the ground state has, so that the winner of the competition to be the ground state becomes a very geometrically distinct kind of location? Does chaos reign in a loose sense? That's a question I want to pose. So Sourav Chatterjee wrote a monograph 10 years ago in which, this is just a crude summary, for a fairly broad class of models of a certain type of Gaussian disorder. Basically, there are these notions of superconcentration, chaos, and multiple valleys that, loosely speaking, correspond to giving yes answers to the three questions I just posed. And the view is that within this class of models, a yes answer to one question ensures a yes answer to the other questions. And my talk explores in a high level of detail, in one sense, a specific model of this. It can be construed in those terms. So onset of chaos in a dynamical form of last passage percolation. That's going to be the theme of the talk. I'll obviously be explaining, defining these terms more precisely. Okay, so the three aspects. I'm going to tell you about Bernoulli last passage percolation. I'm purely doing that for reasons of exposition, and I hope clarity. It is not the actual model that will be studied in the rigorous setting. Indeed, it's not an integrable model. We have an n by n box in the plane, and the integer sites therein are, in the static version of the model, assigned 0 and 1 values according to independent flips of a fair coin. We have a notion of an upright path that runs from the southwest corner to the northeast. It's only permitted to make its move east in an easterly or northerly direction. It accumulates an energy, which is the number of ones it comes into contact with according to the random assignation of value. So each upright path is assigned an energy in this manner. Bernoulli last passage percolation. So the geodesic is the path on that route of maximum energy, and of course in practice there's more than one. There's exponentially many, I think. But anyway, it serves my purpose to simplify things and speak of the geodesic. The actual energy of that geodesic, the weight or geodesic energy, let's call that Mn. N is the system size, okay? And that says, gamma n, okay? That's the path. So superconcentration is reflected here. Okay, so if we look at the maximum energy, it is naturally enough growing linearly, and it's growing linearly with a coefficient that beats the coefficient I would get for a ordinary path, which would have a value of 1. That's kind of an intuitive statement, I guess, that that's true. Now, if we had a Gaussian fluctuation, that would, CRT style, we would have an n to the 1/2 fluctuation, but we have a more concentrated situation than that, in which the Wn random variable here is an object that is tight and non-degenerate when viewed as a function of n. So this is superconcentration illustrated, okay? Oh, and by the way, this is it's obviously not a rigorous statement. This is what is expected for this model. It's, as I say, for expositional purposes that I say this. Okay, so what about speaking of an energy landscape for last passage percolation? Okay, so if we consider a problem in which, in speaking of 0, 0 to n there that you see on that part of the slide, that's the route that I've already been taking, I can consider varying that route by making a horizontal displacement of x in the upper endpoint here, the northeast endpoint. I can then look at the correlation I have between the geodesic energies for the two routes. And it's a perfectly natural question to try to identify the scale of the value of x that will result in a kind of a 50%, a theta-1 genuine change, but genuine staying the same type scale for this. And then this is Kadar-Parisi-Zhang scaling coming in here. What is expected to happen? This model being expected to lie in the KBZ universality class is that x should inhabit the scale of n to the 2/3 in order that we see this sort of interesting scale of correlation develop in this statistic. So you see the black and the blue roots, those are the gobbling up as many ones as possible on their respective roots given their endpoints, and this is the scale to have this sort of non-trivial correlation.
This is the correlation between what?
Between the geodesic energies for the roots that both come out of 0, 0 and end at the respective upper endpoints you see in this sketch. Okay?
And so the claim is that when x is that big, these start to become decorrelated.
Yeah, like if you're gunning for 50%, then this is the putative, it's not the right word, the expected scale at which this is anticipated. And for other models, it's known. Okay. So doing that suggests that we might consider a scaled picture. That's just simply a picture of the endpoints on the left that were already drawn. And then an affine transformation would get me to a situation in which the vertical displacement is the northeast long displacement is represented by a vertical journey of 1 unit. And then the horizontal displacement is being kept horizontal but squeezed by a factor of n to the 2/3, so it becomes a unit order distance. So if I take the geodesics I was drawing and draw them in the new picture, I get scale geodesics that, well, actually in one project I was calling them polymers. That's probably not a very good, that term has not Yeah, don't worry about that. Okay, so then, but basically then, in speaking of these scale geodesics coming out of here and landing at x, it's quite natural to interpret this quantity that sits here as being the energy of those in the kind of scaled framework and the scaled coordinates, WNX, that unit order random object, non-degenerate object, that's the energy in the scaled picture. So then you get like a polymer tree picture. There's a simple kind of coalescence property that goes on here. If you take the scaled objects coming out of their respective locations, they're all drawn back to the same one. There is a simple, well, I won't go into it, but there's a simple, almost sure uniqueness in the scaling limit here that means that when guys hook up going backwards, they stay together. They don't come apart again. So you get this tree-type picture. And then related to that tree-type picture is the scaled energy, sometimes I call that the weight, WNX, which is ascribed to the path that ends at x, as I was saying, okay? So then, okay, related then you have that notion of the scaled geodesic tree. I can accompany that picture by this picture of the accompanying geodesic energies. So associated to this point is this scaled geodesic. That has a certain scaled energy, and that value is plotted here as a function of x. And that picture is one that is a locally Brownian picture that is globally parabolic. Right, so if we take a high-end limit, now there's a slight confusion here that Wn is not an object that is known to rigorously exist for this model, but for others it is, and it is known that we have this distributional convergence to an object which is a parabolic shift of the Airy 2 process introduced by Prohofer and Spohn at the very end of the 20th century, I guess. Okay, so what we have there is something that can be, broadly speaking, construed to be in the kind of framework I've been talking about of an energy landscape. A peak energy, that's where you would, the horizontal coordinate at which that peak is attained represents the place you want to go in the scaled environment in trying to do the best you can, going out of a point and ending at that horizontal line 1 unit about, and, well, a rival peak, more or less convincing rival peak to the left there, which is some sort of local maximum for energy. So here's a question concerning the scaled energy landscape. What's the probability of having near twin peaks, i.e. a rival to within epsilon of the energy maximum at distance at least 1? Here's a sketch of that. So this is again a sketch of this scaled energy. If the peak is over on the right there, here we have a relatively rare scenario in which there's a genuine rival that's macroscopically separated. This sense of geodesic, geometrically distinct rivals is manifested in this picture in this context. So within epsilon over on the left at distance at least 1, we have a rival. The claim is that the probability of that scenario for very small epsilon is scaling with epsilon. This is kind of an input for the themes in this talk I'll be developing. So I want to say something about the proof idea for that. The profile I've been speaking of closely resembles Brownian motion on unit order scales. So the estimate here, if this were a Brownian motion on a unit scale, it's not hard to see that this type of phenomenon occurs with this probability. So in a loose sense, it's inherited from Brownian motion, but how do we actually prove that? Well, this is an example of a situation where that object is conveniently embedded in a richer, higher dimensional kind of object that has extra structure to it that can be analyzed and exploited. The parabolic Airy 2 process, the Airy 2 process I've mentioned with this parabolic curvature, is in fact the uppermost curve of an ensemble, a whole ensemble of random continuous curves indexed by the natural numbers, the first one uppermost, the second one next to it, and so on, via the RSK correspondence, which I won't go into here. That's the parabolic version, the parabolically curved version of the Airy line ensemble. Now, that object has a nice resampling property, a nice form of integrability that's manifest in this sort of collective object, not directly in the uppermost curve. If I take that object and, for example, I remove the piece of the top curve between -1 and 1 in terms of horizontal location, and I ask, given the rest of the picture, you can see the undotted black lines you continue to see, what is the conditional distribution of the piece I removed? It's given by a Brownian bridge connecting the endpoints to hook up in the right places, but conditioned to remain above the curve below. This is the Brownian Gibbs property. So that's a powerful tool for proving Brownianity of the Area 2 process. Yes, so these slides were written a couple of years ago. I worked with Jake Calvert and Milind Hickey when they were grad students with me on this and proved this estimate. And then Duncan Dalverne has an alternative approach which gives somewhat stronger results, in fact, for proving this kind of thing. But already a fairly strong form of this estimate was available on the basis of this paper I mentioned. So the takeaway anyway is that we can establish this kind of epsilon scaling that I mentioned for the probability of this rival form of energetic closeness at a certain distance. Okay, another theme I mentioned, chaos. How do we introduce this here? I'm going back to Bernoulli LPP here for expositional purposes. What I propose to do, the theme of the conference, beyond 2D, my excuse for that is, I suppose for me, 2 + 1 dimensions. I'm introducing a dimension of time into a basically planar model. So what I'm doing is proposing for definiteness for our fair coin flip model with the zeros and ones statically there at what I will now regard as time 0, as I'll be having continuous time evolving from time 0 and Poisson clocks independently attached to each vertex. When they ring, we can either flip the bit there or independently resample it. And then we will have a model clearly which at any static given time in the future, t, will have exactly the same distribution as at the beginning. So yes, at the level of the geodesic, clearly we have that at time 0, and now it's natural to introduce this kind of notation, subscript n, for the actual basic extension of the system I've talked about, and then this is the time, the new notion of time. So that then has an accompanying energy where that time is also denoted, and then this object evolves a little bit as time goes on from black to blue, and then we have the geodesic at any given time t and the accompanying energy. Okay? Yeah. So how to measure the fragility of these objects to the passage of time? There are two natural means, perhaps. There could be others, of course. We can look at the covariance as a function of t, that is between the maximum energy accrued on that journey, point-to-point journey across the box at time 0 and at time t. That's the first object indicated here. And then another more geometric view is to look at the, I'm going to pretend that there is a unique geodesic at any given time. That's an inaccurate statement, but it is, I think, a distraction to get into that. Just somehow choose one for definiteness. That's what gamma n0 is. That's what gamma nt is at the later time. How many vertices are actually on both parts? So obviously that starts with the full size of the geodesic at time 0, and it will drop in time, on average, presumably. Anyway, that's geodesic overlap indicated there. That random variable there is a geodesic overlap. Okay. So this is what we broadly might expect. If I look at the covariance, that starts at the basic variance we have in the problem. The variance in the energy is scaling like n to the 2/3, and then that drops over time. Clearly, it's a somewhat trivial statement that ultimately it will drop to 0 because obviously all of the bits would be updated. If we look at it at the level of geodesic overlap, that starts with everyone involved, so that's of order n. I think technically 2n + 1, something like that, is the number of vertices. So we start at that level, and then we in fact drop to a level that's another one of these little KVZ scaling computations to see what it is. The number of vertices that get to participate in both geodesics on average is scaling like n to the 1/3 if I have completely independent samples of the randomness. So that is the level to which we are asymptotic. But these are completely unquantified pictures in terms of the scale on which this happens. I want to address the question of making that precise. So here's the theorem with Shirshendu, my colleague Shirshendu Ganguly. So, okay, there is something called Brownian LPP. I think in these slides I don't emphasize what it is, but basically it's formed from many independent copies of Brownian motion, and one rides through them. There is a natural OU update, longitudinal update on Gaussian random variables and also on Brownian motion, and that can play the counterpart of what I mentioned for Bernoulli percolation, but as a crux in the talk, I tend to emphasize Bernoulli. Anyway, for this analogous Gaussian model, there is this transition from stability to chaos, and it is being measured by the latter notion of geodesic overlap, and the time scale on which it occurs is t is n to the minus 1/3. If you translate that back to the Bernoulli model, it corresponds to, in fact, a timescale I think of, okay, if you did discrete updates, like at each discrete time step, you randomly picked a vertex in the n by n box and resampled it, this timescale corresponds to n squared times what you see, n to the 5/3. So for example, if you take the given geodesic at time 0, which has n vertices on it, this timescale is one in which n to the 2/3 of those vertices have been resampled. Anyway, indeed what I mean more precisely, stability is manifest in the statement that when t is much less than n to the minus 1/3, think minus little of 1, there is a more precise statement, then the geodesic overlap is macroscopic with high probability. So there is a small value of d such that d% of the vertices in the original geodesic are still holding on in the new person feeling the limelight. That's what is happening typically. When we push past this scale, the chaotic regime, the supercritical regime, where t exceeds n to the minus 1/3 in a similar sense, we have seen a drop in the fraction of sites in the original geodesic that still feel the limelight to be little over n. Only a vanishing fraction remained. That is the typical scenario. Okay. There is a more precise statement you can look up.
Can we interpret this as saying something about how rough the profile is, the landscape? Is it like some measure of the Hausdorff dimension of the landscape or something? The graph of the landscape?
Well, it might be related, of course, in and of itself, the landscape as I defined it is more manifest at the static time. So the question would be, you're posing is about some sort of scaling relation that might obtain between the static object and how that would drive the onset of chaos when we noise it. I mean, there are relationships. I mean, if the static landscape has rivals, pretenders to the crown in many different locations, for example, it's more plausible that noising it will cause the onset of chaos relatively rapidly. Okay. So signpost to the proof. Okay. So the transition from stability to chaos, let's broaden it to consider options. I mooted two possibilities for the so-called order parameter by which we will gauge the transition. I mentioned energetic change, and then I actually then focused on geodesic overlap. And indeed, it will ultimately be the case that the latter two statements are the ones that are proved. So we have the subcritical regime where t is much less than n to the minus 1/3, and the supercritical one where it's much bigger than that. So basically, I want to take you through something of this. This is a relatively straightforward statement to prove given the state of the literature. It will then go on, in fact, to prove this statement as well, that there's not much change here, and then the substantial technical component harnesses some of those inputs to prove that, in fact, that box down there is available. So that's kind of what this says. Okay. So Sourav Chatterjee's monograph and related ideas in discrete harmonic analysis and Gaussian manifestations thereof lead to an understanding that there is low geodesic overlap when significant time has passed, that there is not much energetic change when we're on the lower side of the transition temporally, and then the substantial component, as I say, of the work with Shirshendu involves establishing that, in fact, at the short times there, it is probable that you have high geodesic overlap. And that is something that harnesses for example, statement 2 is one of several elements that go into proving statement 3 as indicated. Okay. So I'm going to take you through something of this. Step 1, I guess, relates indeed to box number 1 there. So we're supercritical and we're trying to show low overlap. So Sourav's theory of superconcentration and chaos involves Gaussian polymer models. We focus on this Brownian version of last passage percolation, which I haven't actually emphasized in the talk, but it is at the intersection of a couple of techniques.
Define it.
No, I haven't even defined it. I could define it. I take, analogously to the levels I had before, the heights of those levels, I draw a Brownian motion at each, indexed by these levels, and then I go on a journey from 0 to n, in which I'm making my way from, you think of riding the waves, for those who hanker for the beach, from this starting point to here, and then the increment you will experience will be this increment along the first level, and then jump onto the second for emphasis. This is what you get. You go on the journey jumping, surfing the waves from one to the next in order to accrue as much as possible in terms of these increments. That is the object. Okay, so there's a very nice formula that comes from his work that says that the variance of the geodesic energy on the given route I've mentioned has this integral expression in which what is appearing here is the mean value of, this is the geodesic overlap. I've defined it already between time 0 and t. Okay? I was saying though that, Brownian last passage percolation sits at the intersection of two important techniques for us. One is these ideas that are Gaussian in nature in the way that they've been developed, and the other is that Brownian LPP is somehow the perfect precursor to the scaling limit in terms of the KBZ universality class viewed from the perspective of the Brownian Gibbs property. There is an RSK correspondence associated to this model in which I draw a kind of a Brownian watermelon, as it's sometimes called, in relation to the airy line ensemble that I drew, and then that object at the finite level perfectly satisfies the Brownian Gibbs property, which makes it very convenient to analyze. I mean, in the work and the development of the Dalvern, Ortman, Virag development of the so-called directed landscape, the precursor model there was also Brownian LPP, I think largely because in order to gain enough understanding of that object geometrically and probabilistically, it was convenient to harness the kind of Gibbs properties also. All right, so simply because if you eyeball that formula for a moment, you can make an inference from the information which is available in the Brownian setting, that the variance of the energy at a static time is n to the 2/3. It basically forces, it's also known in fact, and it's relevant I think, that the mean overlap quantity you see here is monotonically decreasing in t in fact. And that forces, it's simply incompatible for this object to remain high in the relevant scale as t advances through scale n to the minus 1/3. It would simply cause an accrual of too much value here. This is a very, this term can be ignored because the way the scalings work, so think of it as a simple integral. This has got to drop down somehow in order that we do not report too much value. So, given the state of play anyway, this can be seen as a direct inference from what's known, basically. All right, so then I think we want to look at box 2, so subcritical stability of geodesic energy. That I want to present in terms of discrete harmonic analysis, and again, for that purpose, it's quite fun to look at it in a Bernoulli setting. Okay, so, all right, a slightly different notation perhaps, but I'm now saying MNT, you understand, is the geodesic energy in the Bernoulli model, in its dynamic manifestation on this standard route we've been talking about, okay? So then, if I take an object of interest for energetic change, of course, well, directly that is the energetic difference between time 0 and t, I square it and take the mean, I'm making this claim that up to a constant factor, this is bounded above by t times n. So if I then look at t, that's tau is kind of a scaled form of time. If we anticipate this is the relevant scale for dynamic change, then tau represents scale time. So if I then take tau a little bit less than 1 somehow, then this is compatible with proving this, because this object is of order n to the 1/3. So, well, it's compatible. I mean, we're squaring up, so this is somehow a kind of n to the 2/3 thing, and then the scale is right to be saying that this is true when tau's responsible for the little o here, I think. Okay? So a key technique for proving this claim is discrete Fourier analysis that was, for example, responsible for proving some beautiful results about the model I had with hexagons and the updates, Petter, Schramm, Garbon, for example. Okay, so we take our zone of interest in this model, which is this box, and then I can view a geodesic energy clearly as a map that assigns to each assignation of zeros and ones to the box a value. So the value 4 is assigned to this setup because the 4 is the maximum number of ones one can collect on that journey, the upright journey from southwest to northeast. Okay? Okay. So then we have kind of a Fourier representation here in which for each subset of bits in the box, I can define a function here which is, so omega here is the assignation of ones and minus ones, and then this product, or maybe it's an assignation of ones and zeros rather, and then this is the accompanying assignation of ones and minus ones. So I'm just taking the product here. I'm concerned essentially with the number of zeros that are attached to a subset S of interest and its parity. So this object is returning the value plus or minus 1 according to that consideration. So that is in fact an L2, it's an orthonormal basis for the L2 space of functions mapping these assignations of zeros and ones to vertices in the box to the real line. And then we can then start to decompose functions of interest, including the geodesic energy, which is a function, after all, of all the 0, 1 assignations in the box it reports value. It has a kind of Fourier representation on this basis, in which the indices are subsets of the vertices in the box. Yeah. So Parsifal's formula takes this form, and that allows us as probabilists to view this as a probability experiment in which a random variable, which takes values in subsets of the bits in the box, it's a random sample thereof according to a measure Q, according to this formula here. Okay, it's just simply that these numbers add up to 1. So we randomly pick a subset of bits in the box, the spectral sample, and then it's relatively simple to prove this fundamental fact about the relationship between the spectral sample, its role in studying dynamics. If I take a given time t, then I have this formula for the covariance of the function of interest, which specifies the function of interest specifies the spectral sample via the Fourier coefficients. And then we see this exponential penalization of Fourier coefficients according to the size of the indexing bit space. And then you have if you're studying covariance, then it's a question of looking at the mean value under the spectral sample of this object. So this is an object that is basically cutting out the high frequencies in the Fourier space as a function of time. At a certain time, we start to see a lack of representation on the part of those Fourier coefficients whose size is significantly larger than 1 over the value t in question. So if we have a situation of a function in which there's a significant representation in the Fourier basis at modes of very low cardinality, like the dictator function when we do an election, then that would be something that would be rather a stable situation. Whereas if everything's up above a certain level, then that we simply see low covariance and close to 0 correlation as t pushes past the reciprocal of that cardinality of that scale. So, okay, I want to argue for the purpose of, for my purpose to argue that the typical size of the spectral sample for the problem of interest is behaving like n to the 1/3. And then that combines, I think, with something I stated a moment ago in Jensen's inequality to deliver this information, the claimed bound. It's probably a bit hard to absorb the inequalities and process the convexity and so on. I understand that, but I hope you'll, to some extent, ideologically, conceptually take it on faith to some extent that this kind of bound comes out in the wash here. So in terms of keeping ideas compact, maybe just focus on desire to prove this fact. Okay, that's where I'm going next. We've reduced to that, basically. So subcritical energy stability reduces, in fact, to proving this fact, and to the 1/3 scaling for mean size of spectral sample.
And I guess you just need one side of it for your application, just that it's bigger equal or smaller equal, I'm not sure.
Yeah, I suppose so. I think it's concern of, yeah, I think so.
So which one do you need?
I'm not sure I can process it live. Your Ron's penetrating questions will late on Wednesday afternoon too much, but okay. So okay, the technique here is to if you take any particular vertex in our box, then you can think of the function. This is the geodesic energy you would get if you took that very particular bit and you simply flipped its value from 1 to 0 or vice versa, as it may be. And then the next thing I'm claiming en route to proving the n to the 1/3 formula for the left-hand side here, I'm next claiming that this is true. Okay? So I sum over the bits in the box of the mean value of what's happening when I make that change and square it. Okay? So the proof of that, okay, so if I take the spectral sample, the mean size of the spectral sample outcome is given by considering the sum of probabilities over bits in the box of lying in the spectral sample. The definition of the spectral sample gives a certain formula here in terms of these Fourier coefficients. And so on that basis, it's enough to, in fact, we want to rope in this type of expression, and it's basically coming out of here. I think in the formula there's a 4 here, so if it appears up here, I can substitute this in. I'm reducing to proving this particular fact about the effect, the mean effect on the square of doing this particular replacement. So we have this representation for a representation of the geodesic energy. We make this change and have this accompanying representation where the value of chi-s, the Fourier function at that frequency, is adjusted in a natural way. Well, okay, maybe it's a bit hard to process, but I mean, basically, in a certain sense, it's fairly straightforward computation. If I take this square, I get a difference of terms in which there's a certain distinction between where the vertices lie in the subset S or not. And this difference ends up doubling up in one case and not the other, and leading to this formula. Yeah, so we've confirmed that, and then just to take you through why that gives you n to the 1/3, well, the view is that this is scaling like n to the 2/3, and then I'll justify in a moment that this has a linear scaling. This object here behaves like n, so that is what gives rise to the n to the 1/3 I've been claiming, and to which I've reduced in the style of this talk the statement in question box number 2 in the discussion. Okay, so to say something about why this is true, this sort of remaining fact in this section of the talk to justify. Okay, so I mean, there's a certain amount of notation here, but this is quite straightforward if I'm on the geodesic. If I change the value, particularly I think if I'm on the geodesic with a value 1 and I switch it to be 0, actually it's the more straightforward case is I think if I'm on the geodesic with a value 0 and I switch it to 1, I will clearly make a difference. It will clearly increase the geodesic value by 1 by doing that, and that will report a 1 value here. There are basically n elements on the geodesic, so as a lower bound that gives this n here. This is a bleak answer, I suppose, to Ron's question. I suppose that what's more delicate is to show the opposing direction, the upper bound. And for this purpose, the concern is to argue that when I go off geodesic, I don't pick up significantly more contribution. So I wish to argue that there's only a comparable order, a linear order in n of off-geodesic vertices that have the property that they rarely make a difference. To classify off-geodesic, here's a vertex this is the geodesic in black. This is a vertex off the geodesic. Imagine that this anti-diagonal distance is k. That's a measure of distance to the geodesic. what I want to argue is that we have this kind of bound. The probability that you make a difference if you flip that value there is bounded above by k to the minus 3 over 2. Now, that is enough to establish that the off-geodesic contribution is not greater than the on-geodesic one, because, as it were, there's a at this diagonal coordinate, there's a contribution of 1 coming from the geodesic value. And then when I sum over k, as it were, in both directions, I get a summable sequence. So I sort of get order 1 at each diagonal coordinate, if you see what I mean. So I've reduced everything I'm saying in this stage of the talk to trying to justify this statement, okay? So this is a little bit much to take in, but perhaps, okay. The view is, it's quite a fun perspective in a way that I've rotated picture by 45 degrees, so I can think of going directly upwards here between points with the same horizontal coordinate. This is the geodesic. I cut through at the midlife line here. That corresponds to the anti-diagonal line at the midway point before. And so I have this sort of distance of k here. There's two relevant functions here. One is sort of in some sense rooted at this point, and it runs along here and reports energy you get when you go on a geodesic from this point to any given point here. That's the black line here. There's an accompanying function that's rooted up here, and it reports value here in the same sense. So it's the best energy you can get between this point and a given point here. That's then plotted in blue here, except for I put a minus sign here. I basically turn that function upside down or reflect it in the x-axis. And then what I do is I prop that function on top of the other function so it just rests there at that point. That point at which it rests, its x-coordinate, is where the geodesic wants to run through. So the geodesic runs through here at the resting point, and k units to the left, this is here, there's a certain disadvantage or cost to running through this location instead of this one in terms of accrual of energy on that route. And that wastage deficit is the distance between the black curve and the blue curve at this point. So were it to be the case that there would be, were it to be the case that there were a contribution coming at this level, it would mean there would have to be actually a touch point here. It's a bit like the near touch discussion we had earlier on. The probability that the black and blue curves touch at this point, in fact, scales like k to the minus 3 over 2 if you accept the correct heuristic, or the widely accepted heuristic that these objects look locally like random walk, and view this as a random walk problem, something that is known rigorously in the accompanying setup for Brownian lost passage percolation. It's certainly not known in Bernoulli lost passage percolation. But this exponent comes out of a random walk heuristic, which can be made rigorous in integrable models of lost passage percolation. So that justifies all of that. So actually, though, that just brings us to the starting point in one sense, that the major technical challenge that Shirshendu and I faced was actually to have a single order parameter over which things would work, which meant either putting a tick in this box or putting a tick in this box and having a complete row. We went for geodesic overlap. So I want to say something about that in the remaining time. How did we actually go about proving that at short times below the putative n to the minus 1/3 scale for transition, that we have high geodesic overlap? That is the remaining challenge. Now, we did that, we harnessed box 2 in order to get this box. We harnessed our understanding that we had energetic stability subcritically. And we did it by something that we could call the proxy. Let me explain. Okay, so it's, as it were, in the style of a proof by contradiction, in the style of showing anyway that low overlap in this subcritical phase is unlikely. Let me give you a typical scenario, or a plausibly typical scenario, for what could happen were it to be the case that there was low overlap at this relatively short time t between the scale geodesics depicted here. And in fact, this is a simplification, and much technical work goes into other cases. But it may be the case, it's a case of interest, that the reason that we have low overlap is shared roots at the beginning and the end, more or less, and then a substantial period in the middle in which routes go their separate ways, okay, at the two different times. So the aim is we have two different times, it's hard to compare them. We want to route things at a given time and harness the tools available for static Brownian last passage percolation. And for that purpose, we find a certain technique for transporting the geodesic at the later time back to time zero by an object that is, whose notation is written here, a proxy. The proxy will mimic the root of the geodesic at the later time, and in its time zero weight, it will rather accurately approximate the time t weight of the time t geodesic. It will accurately mimic geometry, and it will mimic in its time zero weight the time t weight of the later geodesic. It's in one sense defined in a relatively direct way. We choose a bunch of points judiciously spaced along the time t geodesic, and we interpolate them with time zero local geodesics. So these are best paths in terms of the time zero energy environment. And that union of paths is the overall path that is the proxy. Okay, so what we take what we might construe as a typical low overlap scenario like this, in which low overlap is occurring because of a substantial difference in the geometry, and therefore a significant period, a dominant period of absence of contact between the paths in this lengthy midlife. That then typically forces largely a comparable in terms of drawing the picture scenario, but this is one in which the proxy has a substantially different route to the time zero object. Now, at the level of energy, we've got some information here, because we know from this box 2 that there is subcritical weight stability. That means that these two objects have very similar weight, and I should emphasize what I mean here is the time t weight of this object and the time zero weight of this object, the geodesics at the respective times, are very similar. We know that from the work we've done that I've tried to explain. They differ by little o of 1. Now, the slide doesn't say this, but this is important to recognize that when I speak about weight here, I'm talking about time zero weight. The transported proxy object and the geodesic at time zero are similar in their time zero weights. So we're now in a position to make comparisons in a given static environment. Yeah. So basically, this is what we have. It's rivals. It's an energy landscape with rival peaks because this substantially different route gets almost the same energy. In terms of that upside down picture that I necessarily had to say rather quickly, it has a kind of continuum counterpart here in which this energy profile here has an accompanying upside down energy profile sitting on top of it with the touch point here corresponding to the x coordinate at which the geodesic at time zero passes, but then we have an alternative route of passage that is a very effective contender to the crown of time zero energy winner. And that means that there's a near touch here. These curves come very close to touching here. Now that is a problem that's basically very similar to what I said earlier. The Twin Peaks event is very similar. What's the probability? A parabolic Airy 2 process, more or less the same on the relevant scale as a Brownian motion, has this rival Twin Peak event of a unit order distance between these points, but this point coming within epsilon here, as I explained, that's of order epsilon. And so that then leads into, that is a rare event, in short. I haven't said what epsilon is when you work it through, but there is a diagnosable abnormality or rarity manifest in the time zero environment delivered by this type of estimate. So in summary, the proxy has transported the geometric scenario typically found in low overlap between the time zero and time t geodesics for a subtypical timescale to a provably rare Twin Peak scenario at time zero. And that's how we're getting our box here and getting our theorem of an order parameter and a sharp transition from stability to chaos in a dynamical form of last passage percolation. And that is it for what I plan to say.